Hey everyone, so this video is going to be talking about interference and one of the very important applications dealing with standing waves. So this is just a recap from the Pogles. There are two, we talked about in phase and out of phase as far as points on a wave, but it also does refer to the to the waves themselves. So you can have two waves that are in phase, which just by the same definition as the points are doing the same thing at the same time. So you have two crests coming together, or out of phase, meaning they would be doing the opposite. You could have a crest and a trough coming together. One thing I want to point out with the in phase, two troughs would always also be in phase. When two waves are in phase, they'll combine their amplitudes together, add up, and you get constructive interference. When you have out of phase, they're doing the opposite thing, and their amplitudes would end up subtracting, decreasing compared to before. Sometimes when you get it completely zero, they'll call that 180 degrees out of phase. All right, so here's a question. Pause video, work on this yourself. I'll go over it in a second. All right, so this is a top-down view of water waves. They have a bunch of crests, which are represented by these solid lines, and a bunch of troughs represented by the dotted lines. And they want to know what is occurring at point P. Well, wave A, by the time it gets to point P, is going to have a crest. Wave B, by the time it gets to point B, is going to have a trough. A crest and a trough, those are two opposite types of waves, so these are out of phase. So the type of interference would be destructive interference. All right, here's the next video, question. You can pause the video, work on this stuff. Go over it in a second. All right, so for part A, they want to know what would create maximum destructive interference. So we're looking for two opposite points. A are two dotted lines, so those are not opposites. D is two solid lines, those aren't opposite. C is just nothing. It's like in the middle of the sets of waves, so that wouldn't be anything. But point B is right here where a dotted and a solid line cross. So this would be maximum destructive interference. Question B, where it says which point is maximum constructive interference, we're looking for two lines that cross that are the same thing, both solid and both dotted. The only time that would occur is at point A and point D. So both of these are constructive interference. This would be with two crests together, and this would be two troughs together, but it would still be constructive interference. This one's a little bit tricky. You need to try to visualize it as best you can. Pause the video, work on this stuff, and we'll go over in a second. All right, so the first, I'm going to try to conceptually explain what's going to happen, and then I'll show you an example. So here they have two waves coming together, and they want to know what point P does. So we need to figure out, is by the time these waves come together, is this going to be constructive or destructive interference? Well, this left hand wave has a trough coming towards it. This right hand wave has a crest coming towards it. A crest and a trough, I'm ignoring everything else because it doesn't matter, but a crest and a trough meeting at point P will be destructive interference. They have the same amplitude, so if they're going to subtract, that leaves me with nothing. So the answer is point B does nothing. Now I have a little quick little animation here, not that one, this one, where I'm going to make two waves, pretty much exactly like from before. There was a trough on this end and a crest on this end. Point P is going to be right in the middle, and if we look at it, that point where my cursor is does not need to move as this wave passes through it, because at that point the waves are constantly destructively interfering. So point P does not move. This ends up becoming really important, mainly because constructive interference is where we get really nice, loud, full sounds. Typically, movie theaters, stadiums, music halls, they tend to try to make sure that there's a lot of constructive interference happening, and there's not that much destructive. That's why you'll notice that they're usually designed very weird, so that there's so much waves bouncing off that for the most part it's very constructive interference type setup. Sound canceling headphones usually work on the concept of destructive interference, finding the noise that you don't want and then trying to cancel it out. There's something that can be created. I just want to, you may not need to know this, but it may help with some of the questions. But if you take two speakers, put them side by side, you can notice some constructive and destructive interference. When you pass by, you'll actually notice areas where the sound gets louder and then it drops. If you were to do this at home, you'd have to make sure that both speakers are tuned the same way and are making the exact same note. But pretty much what happens is when you have two sources like this, as they go out and they start spreading outwards, they'll start to overlap. And when they overlap, the areas where their crests meet, which is this brighter section in the middle, this brighter section here, will be creating constructive interference. And then if you see these black lines that kind of go in the middle, that kind of break it up, those are destructive interference. That's where the two waves are meeting opposite each other. So the crests and the troughs are meeting. This is going to lead us into something called standing waves. So standing waves occur when we have two waves that are interacting, and you get these constant constructive and destructive interference that results in a wave that just doesn't look like it moves. So if you recall with the images that we've shown before, you can clearly tell a wave is moving to the right or it's moving to the left. Here, this standing wave just kind of flip-flops back and forth. So you can't really tell whether it's going left or right. Going back to little animations that I have. So this is a standing wave. When I enable ghosting, you'll see the two waves that make up the standing wave. The purple wave is moving to the left. If you keep your eye on the crest, you can clearly see it moving to the left. For the green wave, you could clearly see it move it to the right. And then the black wave is what we would normally see, and you can't really tell it's moving left or right. So this is an example of a standing wave. For the most part, I don't put it in here, but for the most part, there are 2 points that are important to note. Instead of talking about crests and troughs, because you can see that this crest turns into a trough and back and forth. So what we do is we call this point an antinode. A-N-T-I-N-O-D-E, antinode. It basically is referring to a point on a standing wave that moves the most. The other point is this point here. These red dots are the points that don't move at all. These are what we call nodes, N-O-D-E, nodes. You could think of it as no displacement. So the nodes occur where it crosses pretty much the zero line, that equilibrium line, and then the antinodes are the crests/troughs. So this entire thing would be one antinode and two antinodes and so on and so on. All right. So try to use that to answer these two questions. Pause the video, work on the self, go over in a second. All right, so what produces a node? Well, if we go back to my little animation, this is a node. And if you look at the green and purple waves, it's always when the two crests meet and when the two troughs meet. That is constructive interference. So, this is for the antinode. The antinode is created by constructive interference. The node right over here is where the crest of one wave and the trough of the other is meeting up. So you can see the crest and trough. Where is it? Crest, trough, always canceling out. So this would be destructive interference. So the node is being created by destructive interference. Antinodes are being created by constructive interference. All right, here's the next part. You can pause the video, work on the self, go over in a second. All right, so with this, it's a little bit easier to see, but we have a node here and a node here. Now, when this pauses, remember a full wave goes up and then down. So crest, then trough. So this entire thing is one full wave. A node goes from here to here. That is half the distance of one full wave. So from one node to the next node, that's half a wave. Well, it actually turns out that the same thing applies for the antinodes. So this is one antinode, and then this is the next antinode. That is, once again, half a wave. Pretty much from with the standing waves from one point to the next similar point, it's going to be half a wave. So nodes and antinodes occur at every half a wave. Half a wave, 1.5 waves, so on, so on. All right. So a quick question that you could ask yourself is this. Imagine we have a string that's fixed at two ends, and we're creating a standing wave, and we want to know what's going to be occurring at the ends. Is it going to be node or an antinode? Now again, they're fixed, not moving at the two ends. Well, it turns out that we only nodes can exist on a string. So like for example, a stringed instrument. If you're playing like a violin or a guitar or something, that's an example of fixed at two ends. So when you create a standing wave in there, just strumming on the string, you're creating a half a wave, something that has a node at two ends. As you've probably seen in some of the in the Pogles, the frequencies will actually increase as we go to each harmonic. So the first standing wave you could produce would have a frequency of 5 hertz. Then the next one would be 10 hertz. The next one's 15 and 20 and so on and so on. This is something that's going to be a common pattern. You know, if our first one was 8, then the next one would be 16, 24, 32, 40, so on, so on. So whatever this first harmonic is, each subsequent harmonic is going to be just some number times that. 2 times the first number, 3 times the first one, so on, so on. Typically, we end up calling this first harmonic the fundamental frequency. So the harmonics are basically all the frequencies that are representing pretty much the same type of scenario. In music, harmonics are referring to all the frequencies that would represent a C note. Anyone who's musically inclined knows that they can hear a note and automatically tell whether it's an A note, B note, C note, and even if they're different pitches, different frequencies, different octave scales, they would still know what type of note it is. A lot of that's coming from the fact that it's similar harmonics, that every C note is a harmonic of a common frequency, of a, if you will, a common ancestor. Yeah, once you find the fundamental frequency, you end up finding all the other frequencies that make it up. Alright, so here's a question. You could pause the video, work on this self, and then we'll go over in a second. Alright, so in here we have the standing wave. They want to know how many nodes are there. Nodes are where they cross, where there's no movement. There's 1, 2, 3, 4, 5 nodes. So 5 nodes all together. If they want antinodes, it would be the bubbles. So 1, 2, 3, 4 bubbles. They want to know what the wavelength is. Well, starting at the end, I have to go up a crest and down a trough. So 1, it would be right here. Up a crest, down a trough. 2 waves. So this represents 2 full waves. So the wavelength, if 4 meters fits 2 waves, then 1 wave would be 2 meters. For part C, they want to know what the frequency is. So the frequency is going to be found by doing V equals F lambda, taking the speed that they give us of 10 meters per second, and using the 2-meter wavelength to get that the frequency is 5 hertz. All right. Okay, so they want to know which harmonic this is. So if you paid attention in the POGL, the first harmonic would look like this, just one bubble. The second would be 2. Third would be 3. So this is the fourth harmonic. And then here where they want to know what the fundamental frequency is, well, since I know that this is the fourth harmonic, and I know that this is 4 times the fundamental, I can just say that the fundamental is going to end up being equal to 5/4, or since, fractions are bad, 1.25 hertz. All right. The last thing that I wanted to mention was this concept of resonance. So resonance, basically every object has a natural frequency that the atoms in it will vibrate at. So strings, when they're tight, when you pluck them, they vibrate at a certain frequency. This is called when you match their frequency, when you match this natural frequency of theirs, it's called resonance. So a lot of times you can make a sound, bring it towards something and cause it to vibrate, and now it's caused by resonance. A good example, again, for the music people, if you have a tuning fork, you strike a tuning fork and you place it next to a string. If they have the same natural frequency, then as the tuning fork vibrates, it will start to push on the string, causing it to vibrate. The best way to think about this is that it's like a person pushing someone on the swing. Every time the first object, the source of the sound, is vibrating, it's pushing the air around, just like you push someone on a swing. And every time you push them on the swing, you cause them to move faster and faster and higher until they're basically vibrating on their own. So as you resonate, you end up increasing the amplitude more and more and more until it becomes bigger and bigger. Now, of course, there's a limit to how much everything can vibrate. After a certain point, what's going to happen if you keep increasing the amplitude and increasing the size of the wave in a naturally occurring object? Well, it's going to end up breaking. There's two very common examples. I recommend looking at these. I'm not going to play the videos right now. There's this one. It does have a funny reaction from him, but he does the typical trying to break a piece of glass with his voice. And then this is a very famous and dangerous example of resonance called Galloping Gertie or Tacoma Narrows Bridge. Basically, same thing. The wind blew, resonated with the natural frequency, and caused the bridge to vibrate. So both of these are examples of resonance, and that objects will end up breaking. Well, it turns out that all objects have a natural frequency, even people. There's actually people, scientists during, I believe, World War II, that were trying to develop sonar weapons that would actually naturally vibrate at the frequency of a person's body in order to cause harm to them, to like burst eyes and kill people. The good news for those who are thinking about freaking out is that while every body does have a natural frequency, each person is different, and it's also different depending on which body part you're talking about. A person's eye has a different natural frequency than their liver or their heart. And like I said, each person, because as we all know, not everyone has the same eyes, each eye will have a different natural frequency. So unfortunately, it wasn't super viable. All right, that's it. If you have any questions, please let me know. Otherwise, I'll see you later.